Okay, maybe we should start. First, welcome to the colloquium. I have the pleasure of introducing today's speaker, George Fuller. He's a professor of physics, a distinguished professor of physics at UC San Diego, and I've actually known him since he was a graduate student. George did his PhD with Willie Fowler at Caltech. In fact, he was Willie's 50th thesis student and also Willie's last student. The young people here may not know who Willie Fowler was, but he basically invented the theory of nucleosynthesis and won the Nobel Prize in the mid-'80s for the work that he had done. George's work during that period was on weak interactions. How do weak interactions operate in thermal environments of stars? His thesis, I think, led to 3 papers with Willie, and I think today they have over 2,000 citations, so that was quite an influential thesis. After George finished at Caltech, he went off to the University of Chicago as a McCormick Fellow. From there, he joined Lick Observatory as a research fellow, and then became an assistant professor at the University of Washington. After that, he became a staff member over at Livermore at the Institute for Geophysics and Planetary Science. And in 1988, he moved to San Diego, where he's been there since. While at San Diego, George was the director for 15 years of CAS. CAS was the Space Sciences and Astrophysics Institute at San Diego. And throughout the period from when he joined San Diego to now, he's been one of the pioneers of an area that today is called multi-messenger astrophysics. In particular, George has done some of the most influential work in the field on both neutrino physics and aspects of dark matter. The Shih-Fuller mechanism is one of the ways that sterile dark matter from light neutrinos can be produced in the Big Bang. And in recent years, he's studied the problem of the very nonlinear coupled, quantum entangled, coupled, flavored problem of neutrinos trapped in the middle of a supernova or at the core of a neutron star merger. In fact, that work led to him receiving the Hans Bethe Prize in 2014 from the APS. So please join me in thanking George for coming and giving us this seminar.
Thank you, Wick, for that wonderful introduction. I hope this talk lives up to that. So I gave this a funny title because it was a little quote that Willie Fowler put on one of his papers. Is telling Wick they don't let you put, or at least they don't let people like me put quotes on papers anymore. And it was a quote that it was a paper about the collapse of supermassive stars, and I'll talk a little bit about that. So I think there are several outstanding problems in physics, of course, but the ones that stand out to me are dark matter, we don't know what that is, and black holes, either very small black holes, if there are any, that we might have trouble figuring out how astrophysics would make, and certainly very large black holes, because there seem to be black holes with masses of order 10 to the 7 or higher solar masses very early in the history of the universe, and it may be very problematic for standard astrophysics to make them. You're remiss in any talk on big black holes unless you mention little red dots from the James Webb Space Telescope, for example, which can be interpreted as maybe black hole stars, where there's a fairly large black hole, 10 to the 4 solar masses, and a dense envelope of baryons on top of that. So anyway, we don't know where those come from, and that may also be a signal for non-standard model physics. The dark matter issue is just staring you in the face. The baryons, the world we know of, the standard model, is only accounts for something of order 5% of the total mass energy that we know exists in the universe now. We know that just from gravitation and the CMB observations that we make. And so this is astounding. We don't know what 95% of the world is made out of. We tend to be kind of arrogant in this business, but you can't really be arrogant in the face of that datum. Okay, so if we look at the slowly moving contributions to dark matter, baryon rest mass is of order 20% of that. But the remaining 80%, the stuff we call dark matter, we don't know what it is. And so maybe it's more accurate to say that everybody knows what it is, and everybody has their favorite candidate for what dark matter might be. Might be a particle. Particles include axions, and axion-like particles. Our favorite for a long time was a weakly interacting massive particle, a WIMP. It could be heavy sterile neutrinos for all we know. Actually, we kind of can constrain that with X-ray astronomy very nicely. And it may be kind of asymmetric. You might say, well, 80% is not that much different from 20%. So maybe there's a dark sector, for example, where we're making a net dark baryon number, kind of like the standard model baryon number, which we don't really know where that comes from either. So what is the standard model? Here's the standard model. Here's the zoo of particles, 3 elementary particle families, 2 quarks in each, a charged lepton in each, and a neutrino in each. And we know what the masses of these particles are, and we know what the masses of the force carriers are and how that works. We actually don't know what the masses of the neutrinos are, and they're anomalous in a number of ways. They have no electric charge. Their masses are tiny compared to the masses of the quarks and charged leptons in their respective families. We don't really understand that. In this chart, they're labeled by flavor, electron, muon, and tau. And that really gives you how the neutrinos interact with matter. That's different from the mass states of neutrinos, the energy eigenstates of neutrinos, which are different. And the fact that those differ mean that the neutrinos can oscillate in flavor space. So you produce a beam of muon neutrinos and some electron neutrinos appear in that beam. And we've measured that. We know about that. So let's say a little bit about neutrinos. I can say this, you can read that. They're cosmic tricksters, I'll show you why. There's a lot we don't know about neutrinos. We don't know, for example, where the masses come from. Not the way ordinary charged particles would acquire mass from the Higgs, so some extension of the Higgs, something different. Seesaw models, those involve right-handed heavy states, so that's funny. We don't even know whether the character of neutrinos are, whether they're Majorana or Dirac, whether a neutrino is its own antiparticle. If you flip its spin, does it become an antineutrino, for example? Or does it become something different, a right-handed neutrino that doesn't couple, some kind of sterile state? We don't know where the baryon number and lepton numbers come from. In fact, we don't know really what the lepton numbers are. There's a lot of new experiments, which I'll summarize in a little bit, that may give us some handle on this. We have the mass square differences for neutrinos, and we have the vacuum mixing angles. We don't know whether the masses are arranged this way or this way. All we measure from the oscillation experiments is the mass square difference, the difference of the squares of the neutrino mass eigenvalues. So there's a lot that's unknown. And in immortal words of Donald Rumsfeld, there may be unknown unknowns as well as known unknowns. So the situation is really interesting right now because there are a lot of experimental and observational probes of neutrinos coming up. Long baseline neutrino oscillation experiments like DUNE, for example. Neutrinoless double beta decay experiments. I talked to a couple people about that today. The high energy, ultra high energy neutrinos, PeV or multi-PeV neutrinos that are being detected in the IceCube detector. X-rays, as I said, are our best way of constraining whole areas of this right-handed neutrino physics. The big one I can see coming up is one that UCSD and UC Berkeley share, and that's the Simons Observatory, which is a high precision cosmic microwave background experiment that will give us possibly some real insights into what's happening in the cosmic neutrino background, the C nu B. The physics there is to turn the CMB, the cosmic microwave background, understand that well enough and understand the physics of neutrinos so that we can turn that into a probe of the C nu B, which is very hard to probe directly. Okay. So what I want to talk about today is really the interplay of the weak interaction and gravitation. Here's my definition of a star. This irritates a lot of astronomers, I know, but I'm sorry. Here's my definition of a standard model star: a self-gravitating configuration that manufactures or has manufactured its own neutrons. Okay. How do we know this works? Cue Hans Bethe. Figured out how stars shine, at least how they shine for a long time. And so the key is the weak interaction. you have to turn 4 protons into an alpha particle. To do that, you've got to turn 2 of them into neutrons. That involves a weak interaction. So that's where we're going with this. And it seems a little funny that stellar evolution is really driven by this weak interaction, which is, after all, 20 orders of magnitude weaker than electricity at the kind of energy scales we're working at, MeV scales. So you need really big detectors to see them, either from reactors or from the sun, for example, and everybody knows that story. But not many people understand this story. The neutrinos are benign when it comes to stars like the sun. In fact, stars make this Faustian bargain with neutrinos that, hey, let's have the weak interaction to turn some protons into neutrons. That works great for stars like the sun. But for heavy stars, 10 times the mass of the sun, it isn't a good deal, as we'll see. Okay, so there's the T.S. Eliot quote. He didn't, as far as I can tell, he knew about neutrinos and he was writing about them. Okay, so hydrostatic equilibrium. If I have a star that's sitting there like the sun, then we could look at a fluid element in the star and add up all the pressure forces on it and set those equal to the gravitational forces. And if they balance, we call that hydrostatic equilibrium. And we can write down a differential equation. If we know what the relation between pressure and density and temperature is, we can back out what the structure of the star, what the distribution of density and entropy and temperature is. Okay? But that hydrostatic equilibrium is no guarantee that that equilibrium is stable. Likewise, it doesn't guarantee thermal stability, like convection. It doesn't guarantee chemical equilibrium stability either, in the sense that we're not evolved to the point of equilibrium of the nuclei. So the adiabatic index, cueing Chandra, Sekar, is a way we can get into this and quantify how a star is stable. So the adiabatic index, gamma 1 here, d log pressure, d log density at constant entropy. So the way to do this is you take in your hands, actually don't do this at home, and you squeeze the stellar material very quickly so that no heat flows. So the entropy stays the same. Squeeze it quickly to higher density and ask how much does it push back? How much did the pressure increase? So in a sense, this adiabatic index is like a spring constant. Okay? And if the stuff is made of, that's supplying the pressure, is from particles moving slowly, in a dilute gas, Maxwell-Boltzmann gas, then that adiabatic index is 5/3. But if the stuff is made of relativistic kinematics particles, photons or highly degenerate electrons that are forced up into high momentum states, then the adiabatic index is 4/3. Okay? That's the lay of the land. And then so if you do the analysis of the pulsations of stars, you see that the pressure average value of the adiabatic index has to be bigger than 4/3 in order for the star to be stable. That's for Newtonian gravitation. But now if we put in general relativity, remember the essential difference between general relativity and Newtonian gravitation is that general relativity is nonlinear. So if the gravitational field's a little bit bigger, it gets even a little more bigger because gravitation couples to gravitation. So it turns out that if you do the stability analysis in general relativity, then not only does, now the criterion for stability is more stringent. The pressure average adiabatic index has to be greater than 4/3 plus a term that's of order the Schwarzschild radius of the star, the radius if you compress it into a black hole, and the actual radius. So that's a term that's of order the Newtonian potential. So if I look at a white dwarf supported by relativistically degenerate electrons, this will be like the interior of a pre-supernova collapsed star. That number is about 1 part in 10 to the 4. Okay? That sounds small, but its effects are huge. So again, if I think about the Newtonian gravitation and just pressure from Maxwell-Boltzmann particles, and so I think of the stable condition that's bigger than 4/3. And that's the analogy is like a ball rolling in a well. So if you perturb the ball away from the well, there's a restoring force. Likewise, if I take this fluid element and push it in, push the whole star in, then the pressure forces grow faster than the gravitational force, and there's a restoring force. Now keep Newtonian gravitation, and now say the pressure is from radiation, from particles with relativistic kinematics. You can show that a configuration like that is neutrally stable. It has zero total energy. So it costs no energy to push it in or pull it out. It stays in hydrostatic equilibrium. So if I push the fluid element in, the pressure forces grow, the gravitational forces grow exactly the same way. And so it's like a ball on a flat surface. But if it's got zero total energy and it's scale free, I can push it in or pull it out, now general relativity, even a tiny amount of that nonlinear nature, if I push it in now, the pressure forces grow the same way. Gravitational forces grow a little bit faster than they do in Newtonian gravitation. And so it turns that flat table that the ball is rolling on into this. Okay? It's unstable. And this is the Feynman-Chandrasekhar instability, named because of Feynman and Chandrasekhar, who discovered it independently. Okay? And you can read about that in a book with the title of the Feynman Lectures on Gravitation. It has a foreword by Kip Thorne that will tell you how Feynman came up with this. And it was actually a problem. He taught general relativity, graduate general relativity. It was a problem on the final exam. So, interesting. So, Willie Fowler, who Wick mentioned, had a great terminology for a star with zero total energy like this, okay? He said the star is trembling on the verge of instability, which I think is a wonderful phrase, when the particles that supply the pressure for support have relativistic kinematics, are moving at the speed of light. So I want to mention kind of two of these three kind of initial configurations for stars. So one in this table, one of the sort of ordinary massive stars that give rise to the things that we call core collapse supernovae. So these are stars that start off with masses between 10 and of order 100 solar masses. They have an entropy per baryon, which I'll mention in a minute. In units of Boltzmann's constant, it's about 10. It's kind of similar to the entropy per baryon of the air molecules in this room. And when they collapse, that entropy goes way down because of the weak interaction. And they'll eventually radiate 10% of the rest mass of the core of the star as neutrinos, which is phenomenal. They go unstable because of this Feynman-Chandrasekhar instability and a number of other possible things as well. Rearranging of the arrangement of baryons in nuclei, and also the pressure support coming from electrons the electrons are being captured on protons. So a number of things pick them off. Things I call very massive objects, between of order several hundred solar masses and maybe of order 10,000 solar masses, their entropies are higher, more like 100 units of Boltzmann's constant per baryon. And there, if you, at some point, when you do the thing I told you not to do at home and squeeze the material at constant entropy, instead of pushing back, here the pressure is coming from photons, a lot of it from photons. So instead of pushing back, the photons make electron-positron pairs, and they do so in a way, if you make rest mass of pairs at a modest energy, that rest mass doesn't push back. It's not giving you any pressure. So those stars go unstable, and I won't talk much about them. They're very interesting, but I don't know much about them, and I won't talk much about them. And then if we go up above 10,000 solar masses, it's just this Feynman-Chandrasekhar instability that picks them off, and I'll describe that. And they have an entropy per baryon that's of order 1,000. Okay? They, interestingly enough, will collapse and emit something of order 1% of their rest mass in neutrinos. I mean, that's not 10%, it's 1%. Yeah, but the mass is a whole lot bigger. Okay? All right, so what do I mean by entropy? Okay, well, you can look on Boltzmann's tomb. There it is. And so the entropy is Boltzmann's constant, K sub B, and the log of something like the number of many body states in equilibrium. or the number of degrees of freedom in equilibrium in the system. So for our purposes on this talk, if I talk about higher entropy, so here's a cartoon. If I have 6 blue protons and 6 red neutrons, then each of them running helter-skelter, they each have something like 3 translational degrees of freedom, so 36 degrees of freedom. And now low entropy for that same set of nucleons means that I've forced all of them into a carbon-12 nucleus, and now they move around as a unit. As long as I'm at a temperature lower than the internal degrees of freedom inside the carbon nucleus, then I've gone from 36 degrees of freedom to 3 translational degrees of freedom in this nucleus. So we're going to see that high entropy means that the baryons want to be in free nucleons. Low entropy means they want to be in big nuclei. Okay. Another interesting feature of self-gravitating configurations is that they have a negative heat capacity. So the heat capacity is the heat flow, delta Q, divided by the corresponding change in temperature. Now it's negative for a self-gravitating configuration. So if delta Q is negative, if, for example, we're removing heat by neutrinos, temperature goes up. Why is that? It's because now you've got gravitation there, and you can shrink in the gravitational field and release gravitational binding energy as thermal energy, okay? But notice that even if the heat flow is negative, the entropy follows the heat flow. So that if I extract heat from inside the star by neutrinos, the entropy will go down, okay? Even though the temperature went up. Okay. So if this is a table that I made from the results of Kepler that was published by Woosley and Stan Woosley and Tom Weaver. This is kind of 25 solar mass stars, something like the progenitor of supernova 1987A, which Wick can tell you is our kind of Rosetta Stone for what happens. It's our confirmation that what I'm about to tell you about collapse to a neutron star is really true. Okay. So it burns hydrogen, meaning it's doing hydrogen fusion, much like the sun, except probably on the CNO cycle, not the proton-proton chain I showed you. Temperature is maybe 5 times that of the sun. The density is maybe 20 times lower than the sun. And where the sun burns hydrogen for 10 billion years, this thing burns hydrogen in 10 million years, less than 10 million years, really 7 million years in this calculation. And it burns it to helium, to alpha particles. And then the alpha particles burn up also by triple alpha. It gets denser for that, and it's somewhat hotter, 20 keV to 30 keV, something like that. And in 500,000 years, it burns up the helium to carbon and oxygen. And then you'll notice something interesting. The subsequent burning phases are much shorter. The reason for that is from core carbon burning onward, the neutrinos coming out, the luminosity of neutrinos exceeds the photon luminosity. Okay? You're not really getting any energy out of nuclear burning. You're just dumping all that energy that you're getting, which isn't that much anyhow, into space. Okay? And so you are increasing the temperature because delta Q is negative. You're also decreasing the entropy. Eventually, of course, you get to silicon, and these are, you should put silicon in quotes because there's a lot of stuff there, intermediate mass elements, and they burn to nuclear statistical equilibrium, which sometimes we call iron. And when you do that, the temperature is of order 1 million electron volts. The density is of order 10 to the 10 grams per cubic centimeter. Huge. But what you've done now is you've taken roughly a 1.5 solar masses and you've jammed it into something the size of the Earth. Okay? So the Pauli principle says that we force the electrons up into high momentum states. That's where the pressure is coming from to hold this thing up. But the electrons are relativistic. The electron Fermi energy is 10 million electron volts. The electron rest mass is 500,000 electron volts. So we are trembling on the verge of instability. And one thing or another will shove it over the edge, and it will collapse, as I'll show you in a second. So what I wanted to show you is that massive stars are giant refrigerators. They go from an entropy per baryon of something like 10 units of Boltzmann's constant down to 1. And so sometimes in some calculations of core collapse supernovae, the thing that starts collapsing, even though the temperature is 1,000,000 electron volts, 10 to the 10 Kelvin, the entropy is so low. Entropy of 1 is really cold thermodynamically. The entropy is so low that actually the lattice Coulomb energy is bigger than KT. And so it even though the temperature is at MeV, it's basically a frozen crystalline solid when it starts to collapse. Pretty interesting. So you got this quote unquote iron core. It need not be iron. Oxygen, neon, magnesium cores of somewhat lighter stars can collapse, for example, again, because you're trembling on the verge of instability. You're going from something the size of the Earth with 1.5 solar masses. Once it goes unstable, in about 1 second, it collapses down to something of radius of order. It collapses down to the point where the nucleons touch. And the degrees of freedom that are determining the pressure are those degrees of freedom, not the relativistic electrons. And then it stops, okay? So neutrinos carry the bulk of the energy and the entropy in both the early universe and in these collapse environments and in binary neutron star mergers. And they can do all kinds of things relevant for nucleosynthesis. We have to follow flavor evolution because it's really these charged particle, these charge current, weak interaction charge current interactions that really set the neutron to proton ratio and move energy around. So one of the things that we work on a lot in many of the N3S postdocs, and Wick is involved in this, is trying to understand how neutrino flavor evolves in these environments. And so it's a very interesting, albeit fiercely nonlinear quantum many-body problem. Okay. So what's the upshot for physics here? When this thing collapses, as it's falling in, the entropy is very low. But the electron Fermi energy is very high. And the neutrinos get trapped eventually also. And mostly they're electron neutrinos made by electron capture. And so they have a Fermi level too. They're also degenerate, okay? So here's a question. We know the standard model is incomplete. Is there physics that can tap unknown physics, BSM physics, beyond standard model physics, that can tap into that electron neutrino degeneracy and change those electron neutrinos to something else? There's a huge reservoir of effectively 0-point energy there. So there's been a lot of speculation about secret interactions, we call them secret, between neutrinos. And the reason we call them secret is it's hard to collide neutrinos in a laboratory, right? That's the way physics rolls. You smash one thing into another and look at the debris. It's hard to smash neutrinos into other neutrinos. But the early universe and these core collapse environments do exactly that. Okay. So interestingly enough, so we've looked at this, and this is an N3AS project. Anna Saliga was one of our N3AS postdocs, and now she's at NYU, and she led this collaboration where we looked at exactly this and made a very simple model of some physics that's barely plausible. But there was a lot of speculation about this physics because of what it might do in the early universe, that it might, around the time of CMB decoupling, couple the neutrino fluid and solve all kinds of things like Hubble tensions and things like that. That doesn't work. But anyway, it's nevertheless fun to think about what it would do in collapse. So what it would do in collapse, and there's some scalar particle that's exchanged here, and on the vertical axis there is some coupling, and on the horizontal axis is the mass of the scalar, and we just stipulate that the mass is high enough that we don't produce it on shell during the collapse. And then what happens is that degeneracy of electron neutrinos now gets converted to lower Fermi level Cs of other kinds of neutrinos. And then the neutrinos thermalize among themselves very quickly because of this interaction to a temperature different from the matter temperature. And then as the weak interaction brings those temperatures back together, you generate entropy. Generate enough entropy and you'll start to melt nuclei and change this picture of collapse. So we can look at that, and that purple band of those parameters does exactly that, okay? Interestingly enough, Dune and the forward particle facility for a physics facility rather at Fermilab can actually probe some of this in the near future. So that's kind of interesting and maybe eliminate these crazy ideas. But if I look at this picture on the left, you can see what I mean. The blue curve is the temperature of the neutrinos. Effectively, instantly, as soon as you turn this on, as soon as the neutrinos are trapped and start to interact with one another, then the blue neutrino temperature is much higher than the ordinary matter temperature, which you can see there, T sub E, the electron temperature. But then they come back together, and as they do that, you generate entropy, and the entropy melts the nuclei, and the pressure is different now. And so the core will probably be a little bit bigger. We think what that probably means is that you'll tend to wind up with black holes rather than neutron stars. But we can't say much beyond that because we haven't followed this. It's very difficult to follow this beyond that, okay? Okay. So there's interesting physics that maybe we can get at if we understand this core collapse phenomenon. Now let's switch gears and look at supermassive objects. Okay. So stars higher in mass than 10 to the 4 solar masses. So here the pressure for support is coming entirely from the radiation field, from photons. The structure is completely Newtonian. These are very Newtonian objects. General relativity is unimportant in their structure. But what's always fascinated me about these things, they probably don't exist, but what's fascinated me about them is their stability is completely determined by general relativity. Structure from Newtonian gravitation, stability or instability from general relativity. So if we think of the gas pressure supplied by the baryons, and I put gas in quotes, this is non-relativistic Maxwell-Boltzmann pressure. What is that? It's NKT, number of particles times the temperature. Number of particles depends on whether we've glommed the baryons together into nuclei. Right? So for a given number of baryons, if I have, bigger nuclei, I have a lower N for NKT, and so the pressure will be lower. So we can see right away this is going to be sensitive to entropy. Radiation pressure just goes like 4 powers of temperature. So what's interesting for stability is the ratio of that Maxwell-Boltzmann gas pressure to the radiation pressure. We'll call that beta. Then if we actually then calculate what the average adiabatic index is, it's 4/3 plus this small beta term divided by 6. Okay? So we want to compare that beta over 6 to our criterion for stability with the general relativity correction. So I'm comparing that beta over 6 to this ratio of Schwarzschild radius to radius, of something of order the Newtonian potential. So you can see what's going on here. Sooner or later, this thing is going to be unstable and collapse will ensue. Nuclear burning gets you closer to that because it takes 4 protons, for example, and turns that into an alpha particle. So the mean molecular weight went up. Maxwell-Boltzmann pressure went down. Beta went down. Okay? Okay, so if we have primordial abundances, that's what I want to concentrate on. So what does that mean? That means just helium and hydrogen from the Big Bang. So maybe these things form extremely early in the history of the universe. So that's all they've got. Then they will collapse to a black hole. Collapse is utterly inevitable. Nothing is going to stop them. Nothing is hitting nuclear density and stopping this collapse. But interestingly enough, the entropy is high. So there are plenty of electron-positron pairs, even though the temperature isn't very big. The ratio of photons to baryons is quite large because the entropy is 1,000. And so you can generate a lot of neutrinos by electron-positron pair annihilation. And in fact, the neutrino emissivity, the energy radiated in neutrinos, to give you that negative delta Q, goes like 9 powers of temperature. So as this thing collapses, the temperature is going up. And so all the neutrino energy is coming out just before you make a black hole, because that's where the temperature is highest. Okay? So think of it, you get the shell of neutrino radiation moving out. And effectively, these stars are transparent to neutrinos. So if that shell of radiation could contain something of order 1% of this gigantic mass. So if that shell of radiation is slightly asymmetric, we have a time-changing quadrupole moment, and you can get a gravitational radiation signature that we could find with space-based laser interferometers, especially the SIGO, which is a Japanese instrument that may never get built. But if you're a theorist and look on the internet, you can find ultimate SIGO, which is great because it has an incredible sensitivity. If you look at the strain here, it's phenomenal. It goes down to 10 to the minus 27. Anyway, so it's possible we could find these, and we could see that out to very high redshift, a redshift of order 10. Now the problem, and the wonderful thing about it, is since it's transparent to neutrinos, we know what the gravitational radiation burst would look like, okay? Which may be important for detection. Wonderful. That's a lot of fun. How would you form a supermassive star? Here's the hard part, okay? When Willie Fowler was asked about this, he made this comment. I've tried to make this comment too, but it doesn't work as well. His comment was, I don't care, okay? We'll leave that to the astrophysicists. They can figure it out. Well, there were some ideas on this. One is just a primordial gas cloud that starts collapsing. Problem with that is cooling to get it to collapse. And then if you've got cooling, it'll fragment. So you start off with a 1,000,000 solar mass thing, and it fragments into 1 solar mass or 10 solar mass things. That's a problem, okay? You could grow a lower mass star by accretion. So you start off with something like the sun, and you dump baryons on it like crazy. Here's the problem. Once you get to about 10 solar masses, I just showed you that the nuclear evolution time driven by the neutrino emission is of order a million years, a few million years. So you don't have much time to accrete up to huge sizes. I'd say always start with a black hole. That's possible. And just build up the black hole directly. Finally, Zeldovich pointed out, I think in 1968, that if you have a star cluster that's deep enough in a gravitational potential, well, the stars in that cluster are moving close to the speed of light. Same deal, Feynman-Chandrasekhar instability, called the post-Newtonian instability among the stellar dynamicists, and the whole thing can go down, okay? And maybe tidal disruptions will build up a supermassive star in that situation. Okay. All problematic. So we in particle astrophysics, in faced with problems, we turn to the dark side and look for beyond standard model physics, okay? So one example is the work of Alex Kosenko, who's thought of several different ways we can overcome the formation issue, either by catalyzing molecular hydrogen production by some light particle dark matter decay, or by his recent paper with his student Yifan Zhu and Picker, kind of embedded primordial black hole evaporation. Either way, you suppress the fragmentation of a collapsing cloud. There are other ways you can do this. Haibo Yu, who's speaking in San Diego right now, he's from UC Riverside and is the great maven of self-interacting dark matter, SIDM. You can have gravithermal collapse of this and build up a supermassive star that way. Okay. Now, my student and I have looked at something recently. In fact, one of my first students was Gail McLaughlin. And the first problem I gave her to work on was, hey, if we put dark matter in one of these supermassive stars, does that change the way its stability? And so what we found was actually kind of surprising. The answer is that if you put dark matter particles in that are slowly moving, you've added non-relativistic stress. Even though you've added mass, that non-relativistic stress behaves differently. And so actually you can kind of push off that Feynman-Chandrasekhar instability. And this was, several people in Russia, especially Vishnavani Kogan, looked at this as well and came to the same conclusion. My recent student, Kyle Kerrer, has done this in some more detail, and there's a lot of stuff written on how one might make something like this. Mitch Bagelman's work and Hemmerle's work, for example. But here's what Kyle, my student, found. Even a modest amount, or modest is in the eye of the beholder, there's a question mark there. So this is like 0.1% of the rest mass of the star in dark matter contained in the star. And now you can push off that instability. The instability eventually will get you, but when the star goes down, it will collapse on a different adiabat. And so there are interesting questions about whether that gravitational radiation signature might look different. Okay. And also the neutrinos coming out. Ian Padilla-Gay and Kyle. Ian is an N3S postdoc who's recently stationed in San Diego. And so he's an expert on neutrino flavor transformation, as Wick was talking about. And so there's interesting flavor physics in these collapsing objects as well. And the reason the flavor physics is interesting is that since the nu E's and nu E bars have two channels for production, both neutral current channels and charge current channels, as opposed to the nu mu and nu tau neutrinos that have only the neutral current channel at these energies. Well, the fluxes of the electron flavors are 5 times that of the mu and tau neutrinos, so that's interesting. And if we drive a transformation between them, it might change the way energy is deposited, and maybe neutrons are changed into protons. Sorry. Okay, dark stars. Let's now turn to Katie Freeze. We've turned to the dark stars. We've turned to the dark side. Now we're going even darker. We're talking to Katie Freeze about dark stars. So what are dark stars? They're stars that don't burn anything. Not much anyway. Their power source is from the annihilation of, say, WIMPs, dark matter, inside the star. Okay, they have a lot of papers on this. And so recently, after the JWST results, Katie published a paper saying that the UZH object at redshift 10.5 could be a dark star. So my student Kyle and I looked at that and said, nonsense, we can kill her stars. Okay, we're going to kill it with the GR instability. So when we looked at it, it turns out we were wrong. And in fact, there's an interesting interplay between the dark star dynamics, the energy source, and this GR instability. So we've written a paper on this. The point is that if you have a supermassive star supported by WIMP annihilation, it's puffy. It's still supported by radiation pressure, but its length scale is large. Remember, they're roughly zero energy. So we can have them very puffy with a really low central density. And so they're shielded from finding a high enough central density that they would collapse by the Feynman-Chandrasekhar instability. And so here's the interesting thing. You could start off with something like a solar mass star, which again will be puffy. And then you can glom baryons onto that, protons, accrete stuff on it. And then, if you took a standard model star, when you got to the accreting phase where you got like 10 solar masses, then you're in trouble with the weak interaction. This thing would not get there because it doesn't suffer the weak interaction that way. It doesn't get dense enough and hot enough. And so you can keep growing it. Now, eventually the GR instability will get it. And so here are some evolutionary tracks. That's the central density on the vertical axis. On the horizontal axis is the mass of the star. And these are kind of evolutionary tracks in that central density mass plane for various masses for WIMPs. The highest mass is 100 TeV, which is near the unitary limit on this. And you can see that, and the dashed diagonal line there, black dashed line, is where these will suffer the Feynman-Chandrasekhar instability and collapse into black holes. So you can see that they can get there. It's interesting. And if you look at the mass when they collapse, it's relatively insensitive to the accretion rates. Hopefully there aren't any legitimate astronomers that could look at my slide here and see that those are really prodigious accretion rates. But they're the kind of accretion rates that people talk about for black hole stars, for example. Fairly large. Actually, even with less than 10 to the minus 3 solar masses per year in accretion, you can still get these things to live long enough to collapse into a supermassive black hole, or the seed of one. Okay? So in the next few minutes remaining in the talk, let me talk about some more speculative, interesting stuff. What other kinds of stuff could get caught in stars? After all, with dark stars, the first question you ask is, how do I get all that dark matter in the star? So Katie's answer to that is that you formed the star very early on in the history of the universe when the dark matter density was higher. Okay? If dark matter is collisionless, it certainly is higher in the distant past because the density will go up something like the cube of the scale factor. Okay? Inverse cube of the scale factor. Okay. So Then when the thing collapses, it's kind of adiabatic collapse, and it'll pull. Why does it collapse? It's because the baryons collapse, because the baryons can radiate away their energy, and so they can change their phase space density and shrink down into a condensed object, and the collisionless dark matter will tend to follow that, although speed up. Okay. Okay. So we can look at this. We can put particles in, as Katie does. We can put primordial black holes in, kind of like Alex Kosenko does, except we can look at what the heating from evaporating tiny holes would do. Interestingly enough, there are regimes where the evaporation energy can drive off the baryons, and you could get this thing not to explode, but to just zero total energy, just drift away. Are there nucleosynthesis fingerprints in this? This is what my graduate student is doing. Then you can ask, what if there are whole dark sectors of physics that kind of mimic the standard model, except the masses are different and maybe the couplings of the particles are different? So lots of ideas about dark sectors, no real good constraints on them, except what we can get from the CMB. And there's a lot of speculation. If there are light dark sector particles, could they radiate energy away? And similarly change their phase space density and shrink down into an object, maybe very early in the history of the universe. Okay, and so gravitational radiation from inspiraling small dark objects might be a way to probe this. And so Divya Singh, who's an N3S postdoc here, is an expert on that and has been looking at that. That's probably our best way to look at this or to find it. So can we get constraints on the architecture of a dark sector? Obviously, Big Bang nucleosynthesis and the CMB, and what we can derive from that for the C nu B is the best way to go. And we're really looking forward to what we get from Simons Observatory and the higher precision measurements for N effective, for example, and eventually this so-called sum of the light neutrino masses, which isn't that, by the way. But if we can get better constraints on that, then that might be put some real interesting constraints on this. And of course, from large-scale structure as well, self-interacting dark matter, and what we can get from some of those experiments I showed you. But BBN, CMB, large-scale structure, all of that really depends on the history of entropy in the universe. So I want to close with that. So we don't know the history of the entropy in the universe. We don't even really know the history of the entropy in the standard model sector. We know what the entropy is. We can measure it either in the CMB or by deuterium at the time the neutrinos decouple and we get Big Bang nucleosynthesis. And so here's an interesting thing. So the number we get is 5.9 times 10 to the 9 Boltzmann's constant per baryon. So this figure shows something that Alex Kosenko and Chad Kishimoto and I did a number of years ago. So what if we had a particle that decayed out of equilibrium? Out of equilibrium decay dumps entropy in. How do I know this didn't happen? I'm pretty sure I know how this didn't happen, but let's just look at it. Okay, so the entropy starts out more than an order of magnitude lower than the number we measure now, and then the particles decay and they dump entropy in and we get the number, the right number, just before the neutrinos decouple and we get Big Bang nucleosynthesis. How do I know that didn't happen? In fact, our model for the history of entropy is really something like this, but it's not decay of this 275 MeV particle. It's the decay of the inflaton, maybe at the Guts scale, okay? So, but we really don't know. And if we have a dark sector, do we even know that its thermal history and entropy history is the same? What if it starts out colder? So, Vincent Lee, who's another N3S postdoc who's stationed in San Diego, is about to show up here in the next couple of weeks. And so we looked at an extreme case where the inflaton has no dark sector decay channels, only into the standard model. So we reheat the standard model sector from inflaton decay, but we don't reheat the dark sector. We still have gravitational coupling between the two. We share space-time. So there's still gravitational coupling between the particles. And we can make an estimate of what the temperature would be, and it'd be about 1,000th of the standard model temperature. And we can look at the implications of that. And so you can look at the thermal history. The blue curve is what the standard model gives. It's a function of temperature in the early universe. And you can see that the Jeans mass is similar to the causal horizon mass up until the time that the photons decouple. And then the pressure drops and the Jeans mass goes way down and we can form objects. But in a cold, dark sector, that decoupling scale is much lower. And so you could form objects much earlier. So I can then cue Divya Singh again. And so this is what we hope to be looking at some point. So let me end there. Mm-hmm.
We were talking about the dark stars and just how the mass of the dark matter particle, that's changing.
The dark matter particles are finding each other randomly and colliding and annihilating. So dark with WIMPs, there'll be WIMPs and anti-WIMPs. Okay, so the higher the mass of those things, the more bang you get out of a collision. Okay, and the higher the mass means that the lower the number of them, and so the rate of collisions is lower. So that's why it's different. Okay, those evolutionary tracks are different for a given amount of dark matter. Those things, yeah. So the collision rate is going like the square of the density, right? And on the other hand, the actual energy you're getting per collision is just the mass of the particle, twice the mass of a WIMP. So that's why there's a difference in those guys, okay? Right. What's that? Okay, that there's a particle light enough that it can be emitted by a dark baryon. So let's think about this. If we have collisionless particles, then they can shrink, they can fall into a potential well, but you can never change their phase-space density. If they fall into a potential well, they just go faster. That's not good enough. What you're saying is that baryons don't do that, standard model baryons, because they radiate their kinetic energy away in photons, a light particle. So on the face of it, if I wanted the dark sector particles to do this, I would need a light dark sector particle. Now, let's cue what we know we're going to get from, our best constraint on that is from the CMB. It's really from N effective. And so I have to have a particle light enough. If I make it copiously in the early universe, I have to have it light enough that it doesn't blow the bank on N effective. That number you get is of order in MeV, okay, less than that. But now that's assuming the temperature of the dark sector is the same as the standard model. If I start lowering the temperature of the dark sector, I can get away with a heavier particle. I'm playing that game. Okay? What's that? A self-interaction constraint? Okay, that's not a self-interaction constraint. That's just an assumption of how many you could possibly make. That's right. So yeah, in a sense, it is an interaction because the best I can do is have the interaction strong enough that I come to some thermal equilibrium in the dark sector. And so the number density of these light particles is going like the cube of that temperature, something like that. And so that's what contributes to N effective, and that we can constrain from the CMB. So yeah, there's an interesting constraint there. It's not clear we can't evade it. It's not clear we can evade it. So to what? Yeah. Very good question, and I didn't really say. So I made this assumption. I made the assumption that whatever this dark thing is, it's some significant fraction of the dark matter we measure now. Okay? Like maybe all of it. And then so early in the universe, when these things would form, the idea would be that you would have the baryons dissipate and collapse down, and that would drag dark matter with it gravitationally. There's another way you can do this, and we're looking at that with Anupam Ray and Yong Chen, who are also part of this N3AS collaboration. And that's there are kinds of dark matter candidates that interact strongly enough that they can just hit the star and get caught in the star. So the star becomes kind of a catch basin to accumulate dark matter. So this is especially true for neutron stars because their densities are so high. And it's easy to kind of, you can capture dark matter there, and that could add enough, that in some cases that could actually cause that neutron star to collapse into a black hole. So anyway, I know that answers more than your question, but that's what we're trying to do, okay? We would need an interaction between standard model particles and the dark matter in order to do what I just said, that the stuff gets captured. And so then you have to wonder, why haven't we seen it in laboratory experiments? And so it could either be weakly interacting, but not so weakly interacting it doesn't get caught in the neutron star, but weakly interacting enough that it doesn't show up in our terrestrial experiments looking for dark matter. Or you could go the other way. And the dark matter interacts so strongly that we haven't seen it in our terrestrial experiments. Which is what Anupam is an expert in.
More questions? One more? Oh, maybe one. So if there are dark stars, and with the dark stuff that what releases is the standard form. You able to set the limits on the masses, say it's about 7 meters, and the fact that you can see X-ray spectrum.
I don't know. That would be a goal to be able to do that. Right now, in working with my friend Katie, she's just worried that I'm going to say that dark stars can't exist. I tried that, okay? It didn't work. So, I think always with these, per your question also, it's problematic. How do I get enough dark matter into these things to do these wonderful tricks, okay? Now, if I can do that, and I know what the mechanism for that is, then maybe we can get some constraints through what you're talking about.
Any experiments that are show the result? I guess we might observation.
Yeah, so anything that can give us hints of beyond standard model physics. So one of the ones I mentioned was the CMB experiments themselves, which I think have the best chance of showing us that there's something we're missing directly. So there's something about the cosmic neutrino background that's not vanilla and thermal the way we expect it to be. That would be very interesting and might give us clues about this. The other are the short baseline neutrino oscillation experiments, like the SBND experiment, the short baseline neutrino detector experiment at Fermilab, for example, which has a very, very high flux of muon neutrinos. And so that's been touted as maybe a way we can get at some interesting new physics that complements what one might get from neutrinos double beta decay experiments. So some kind of dark, right-handed Z's, for example, or dark Z's that give lepton number violation in some interesting way. I'm sorry? Yes, the Simons Observatory. Yeah, that's right. This is something that UC Berkeley is one of the key participants in, and likewise UCSD is as well.
So let's thank George for his talk.